going to continue our discussion on linear systems. This is the second part of our lecture on linear systems. Last time we talked about singular value decomposition when we talked about how to find the singular values of an m by n matrix A which is of rank R. If A is an m by n matrix of rank R, we can be assured that there exists a m by m orthogonal matrix U. Orthogonal matrix meaning that matrix transpose of that matrix with product with itself, that is U transpose U is going to be the identity matrix, and an n by n orthogonal matrix V, that is which is also an orthogonal matrix, which means V transpose V is again equal to the identity matrix I, and an R by R diagonal matrix D which has got strictly positive elements, and those positive elements are called the singular values of A. So, all these matrices U, V and D, when D is written as an expanded matrix sigma, they can be combined to form the matrix A. So, A is equal to U product sigma product V transpose. So, U product sigma times V transpose is the singular value decomposition of the matrix A. In the most general case, sigma has to be a m by n matrix. However, if the rank of the matrix is equal to m, that is the rank of the matrix is equal to the number of rows in the matrix, then sigma is equal to D0, right. In that case, sigma is equal to D0. However, if the rank of the matrix is equal to n, where n is the number of columns in my original matrix, then sigma is equal to D0, where D is now in the form of a column vector. However, if A has rank R which is equal to m which is equal to n, which means that A is a n by n matrix, is a square matrix, and it has got full rank, then sigma is just equal to D. That is, the matrix is no longer singular, it has got all its eigenvalues are positive real numbers. In that case, we can write, so given the singular value decomposition of A, we can write A transpose as U sigma square U transpose. Similarly, by taking the transpose of that, we can write A transpose A is equal to V sigma square V transpose. Why do we need singular value decomposition? The reason is because many matrices, particularly unsymmetric matrices, their eigenvalues are extremely sensitive to small numerical perturbations. So, small numerical perturbations can lead to large change in the eigenvalues. Such matrices are typically known as ill-conditioned matrices. For such matrices, singular value decomposition is an efficient way to find the eigenvalues of that matrix. Given the singular value decomposition of A, we define the pseudo inverse of A, Ai. Note that this is different from A minus 1, where A minus 1 is the inverse. So, Ai is the pseudo inverse. The pseudo inverse is again defined in terms of the orthogonal matrices V and U, as well as the diagonal matrix sigma. So, it can be written as, the pseudo inverse can be written as V sigma I U transpose, with sigma I is the pseudo inverse of sigma, which is equal to D inverse 0 0 0. Let us recall what was the form of sigma. So, sigma in its most general case had this form. So, the pseudo inverse of sigma is D inverse 0 0 0. In reality, sigma does not have an inverse, right, because this matrix has got 0 elements on its diagonals. It is a singular matrix, it cannot be inverted. That is why we denote sigma I and call it pseudo inverse rather than inverse. So, Ai is the pseudo inverse of A, and we can write it as V sigma I U transpose, with sigma I denoted as follows. So that was our discussion on solving on singular value decomposition. As we discussed, it is very useful for solving problems which are ill conditioned, which have ill conditioned coefficient matrices. Let us now go back to our discussion on linear systems and talk about certain general procedures for solving linear systems. There are basically two main methods for solving linear systems. One method is known as the direct method, the other method is known as the iterative method. In direct methods, we are assured that after a certain number of steps, we are going to get the exact solution in the absence of any round off. And in case of iterative methods, we get a sequence of approximate solutions, and if we continue the sequence to an infinite number of if we continue the sequence an infinite number of times, we are going to get to the exact solution or the true solution. For full matrices, direct elimination methods are the most efficient. However, for sparse matrices, that is where a large proportion of the elements are 0, iterative methods may give useful results with a fewer number of operations than direct methods. For very large sparse systems, iterative methods are preferable. Therefore, what we get from this discussion is that the decision on when to go for direct methods or when to choose iterative methods typically depends on the sparsity of the matrix, that is the number of non-zero elements in the matrix. So, it depends on the proportion, distribution, as well as the sign and the size of non-zero elements. Whether a matrix is full or sparse can be characterized by a property known as the bandwidth of a matrix. A matrix A, for instance, for which Aij is equal to 0, if j is greater than I plus p, what does Aij equal to 0 greater than, if j greater than I plus p mean? It means that all, if we consider a particular row, then all elements in that row which are more than p elements away from the principal diagonal are 0. Similarly, if I is greater than j plus q, which basically means that all elements in a column which are more than q elements away from the principal diagonal are 0. So, in a finite strip bounding the principal diagonal, in the neighborhood of the principal diagonal, the matrix has non-zero elements, while everywhere else the elements of the matrix are 0. And in that case, we say that the bandwidth of the matrix is W, where W is equal to P plus Q plus 1. So, the bandwidth of the matrix is P plus Q plus 1 denoting the principal diagonal. So, this is the bandwidth of a matrix. The number of this automatically gives us the total number of non-zero elements in the matrix, which has to be less than n dotted with W. Sometimes it is possible to relabel the unknown variables in a matrix to reduce the bandwidth of a matrix. Consider this 3 by 3 system. It is clear that this matrix has full bandwidth, that is, its bandwidth is 3. For instance, in the first row the third column is non-zero. So, it has got full bandwidth, it is full, there is no, so the bandwidth of this matrix is 3. So, it has got a full coefficient matrix. However, we will see that by relabeling the variables, it is possible to reduce the bandwidth of this matrix. How is that possible? Well, if we relabel x2 as x3 and x3 as x2, we get a band limited system with a bandwidth of 2 instead of 3. Now, you can see that the maximum number of non-zero elements in a row is 2 elements away from the principal diagonal. The last element is 0 now. Similarly for the row, for the column. So this is my principal diagonal. We have one non-zero element away from the principal diagonal, but beyond that we have 0 elements. So now the bandwidth of the matrix is 2 rather than 3. Algorithms to reduce bandwidth can be used for large matrices. This is because solution of band limited matrices is much less expensive than full matrices. For example, there is the Cuttle-McKee algorithm, which is a widely used algorithm for renumbering the equations in order to reduce the bandwidth. Similarly, there are more advanced versions of the Cuttle-McKee algorithm. There are several other algorithms which can be used for bandwidth minimization. One thing we note is that even if an original matrix is band limited, its inverse may be full. Therefore, if we work on the original matrix and we use a bandwidth minimizer on the original matrix and reduce its bandwidth, but then we try to invert it, we might end up with a full matrix. So, all our work on bandwidth minimization would be of no use, because eventually we have to use that inverted matrix to solve our system of equations, and if the inverted matrix is full, that is going to be as expensive as it is not going to reduce the computational expense at all. Next, we would like to look at a particular type of matrix which are very useful for solving linear equations, which give us a form which is very useful for solving linear equations, and these are known as triangular systems. Recall, an upper triangular system has the following form: u11 x1, u12 x2 through u1n xn is equal to b1, which is the first equation in my system. The second equation has u22 x2 plus u23 x3 through u2n xn is equal to b2, and so on and so forth until the last equation is just unn xn is equal to bn. So it is clear that an upper triangular system has all elements below the principal diagonal 0 and all elements at or above the principal diagonal non-zero. So this system can be solved very simply. For instance, we can easily invert the last equation. We can solve for xn as bn by unn. So it's just one division which gives me xn. So once I know xn, I can use the n minus 1th equation to solve for xn minus 1, because the n minus 1th equation has the form u n minus 1 n minus 1 xn minus 1 plus u n minus 1 n xn is equal to bn minus 1. So if we know xn, we can solve for xn minus 1 using this simple equation just by one division, one addition and one multiplication and one addition. Similarly, we can, starting from the end, we go progressively backwards, and we can use this general formula xi is equal to bi minus sigma uij xj, j is summed over I plus 1 to n divided by uii, for I is equal to n through 1 to solve this entire system. So we start with the simplest equation and work our way backwards to solve for the remaining variables. Similarly, if we have a lower triangular system, that can also be solved very easily. A lower triangular system is one in which all elements at or below the principal diagonal are non-zero, but all elements above the principal diagonal are 0. In this case, the last case was backward substitution, because we solved the last equation and worked our way backwards, while in this case we solved the first equation, which is easy enough to solve, x1 is equal to b1 by L11, and work our way forwards. We solve for x1, we solve for x2, we solve for x3, and so on and so forth. But the important thing to note is that this assumes that the diagonal elements L11, L22 through Lnn are non-zero. Only when these diagonal elements are non-zero can the system be solved sequentially using either forward substitution or backward substitution. For both back substitution and forward substitution, we need to perform n divisions. Why do we need to perform n divisions? Because for each equation we have to perform one division, so n divisions, and we have to perform for each equation sigma I is I minus 1 additions or multiplications. Basically, let us take a look at our equations, and I think that would make it clear. For instance, for solving the first equation, we just have to perform one division. For solving the second equation, we have to perform one multiplication and one subtraction and one division. Similarly, for solving the third equation, we have to perform one division, but then we have to perform two additions and subtractions followed by two multiplications and two additions and subtractions. So, the total number of additions and multiplications for the first equation, we have for I is equal to 1, we do not have any multiplications or additions, so 0 additions and multiplications. For the second equation, we have I is equal to 2, 1 addition and 1 multiplication. For the third equation, we have I is equal to 3, so 2 additions and 2 multiplications, and so on. And if we keep adding the number of additions and multiplications, we will find the total number of additions and multiplications is equal to half n square minus n. And if for large systems, n square is going to be much larger than n, so half n square minus n can be written as approximately equal to half n square. Therefore, backward substitution and forward substitution, we need to perform half n square additions and multiplications. But and the number of divisions is n, but again n is comparatively much smaller than half n square, so the total operation cost approximately is half n square. The number of operations, half n square, is thus almost identical to the number of operations required to multiply a vector by a triangular matrix. Why is that? A triangular matrix has only half n square elements, right? So, if I multiply a triangular matrix with a vector, I have to perform half n square operations. So, the number of operations is identical to the number of operations required to multiply a vector by a triangular matrix. Why do we talk so much about triangular systems? Because to solve an equation using Gaussian elimination, to solve a system of equations using Gaussian elimination, triangular systems are probably the most efficient way of solving it. So, the basic idea is that we try to reduce the system to a triangular system. So, the first part in any Gaussian elimination is attempts to reduce a full system to a triangular system, and once it has reduced it to a triangular system, it uses forward substitution or backward substitution to solve the system. So, the idea is to eliminate the unknowns in a systematic way so that we end up with a triangular system. Let us consider the full linear system, which is an n by n system. The coefficient matrix is of size n by n. A11 x1 plus A12 x2 through A1n xn is equal to B1. Similarly, A21 x1 plus A22 x2 through A2n xn equal to B2, and so on and so forth. Let us also assume that the coefficient matrix A is non-singular, and hence the system has a unique solution. We recall our discussion from last lecture when we talked about the conditions which are necessary for a system of equations to be non-singular. We also assume that A11 is not equal to 0. If we eliminate x1 from the last n minus 1 equations by subtracting from each equation the multiple mi1 times the first equation, where mi1 is given by ai1 by a11, then the last n minus 1 equations do not have any variable x1. So, the size of the system gets reduced to n minus 1 by n minus 1. Let us go back and take a look at our full system and see what we are talking about. So, what we are saying is that the first system, we divide the first equation, we divide all the elements by a11. Then we add a21 times the first equation, we subtract a21 times the first equation from the second equation. We subtract a31 times the first equation from the third equation. We subtract an1 times the first equation from the nth equation. If we do that, the first coefficient always becomes 0, because we are dividing the first equation by a11. So, the coefficient of x1 in the first equation is 1. If we multiply this by a21 and subtract it from the second equation, the coefficient of x1 is going to vanish. Similarly, we do the same thing for the third, fourth, fifth, and so on and so forth until the nth equations. If we do this, then we are going to get the last n minus 1 equations are no longer going to have an x1 term. So, the coefficient of x1 in the last n minus 1 equations is going to become 0, and we are going to get that equation we are going to get n minus 1 equations in terms of n minus 1 variables x2 through xn. So, the new coefficients are given by this, which is just we wrote it in short form in symbolically. So, the reduced system now has n minus 1 equations and n minus 1 unknowns. If at the second stage, after the reduction, the first reduction, we are left with the n minus 1 system, and if it turns out that this a22 is also non-zero, then we can continue with the same process throughout. So, then what we are going to do, we are going to divide this equation by a22. So, the first coefficient is going to become 1, and then we are going to multiply this equation by the coefficient of x2 in the second equation and subtract it from the second equation. So, in that case, the second equation is going to have 0 as the coefficient of x2. Similarly, we will do the same thing for the third equation, and we will continue for up till the nth equation. So, if we do that, we can also eliminate x2 from the last n minus 2 equations by subtracting from the ith equation the multiple mi2 times the second equation, where mi2 is given by ai22 by a222, where I is equal to 3, 4 through n. The 2, the subscript 2 denotes the step in the reduction process. So, 1 denotes the first step, 2 denotes the second step. So, these are the subscript 2 in ai22 and a222 indicates that these are the coefficients of the transformed system after the first elimination. Similarly, we can continue this process, we can continue this for the third step and so on and through the n steps until we get a system like this, which we recall is an upper triangular system. So, from the second equation, we have made sure that the coefficient of x1 is 0. From the third equation, we have made sure that the coefficient of x1 and x2 are 0. Similarly, until we have continued with that process until we have reached the nth equation, where we have made sure that coefficients of x1 through xn minus 1 are 0, and the only variable with non-zero coefficients is xn. So, we have reduced this system to an upper triangular system when we have got a single equation a(n)n xn is equal to b(n)n. Again, we can solve this equation by back substitution. We solve for xn, substitute that in the n minus 1th equation to get xn minus 1, substitute xn and xn minus 1 in the n minus 2th equation to get xn minus 2, and so on and so forth until we get all the variables x1, x2, x3 through xn. So, in the above, aij1 and bi1 refer to coefficients and right hand values for the original system. bi1 refers to the right hand values after the first step in the reduction procedure. Similarly, bin would refer to the right hand values after the nth step in the reduction procedure. The right hand side of B is transformed exactly in the same way as the columns of A. Hence, the description of the elimination is simplified if A is augmented to include B as its n plus 1th column. Basically, we move the right hand side to the left hand side with of course with a negative sign, and that resulting system is called an augmented system. So, if it is required to solve several systems of equations with the same coefficient matrix A, that is, we are interested in solving several systems ax1 equal to b1, ax2 equal to b2 through xn equal to bn, that is, the right hand side is changing, but the coefficient matrix remains the same, then we can augment A by including the additional p columns b1, b2 through bp, and increasing the size of the matrix from n by n to n by n plus p, n by n plus p. So, after elimination, we will have to solve p triangular systems for each of the right hand sides b1 through bp. Let us look at a simple example. Suppose we want to solve this system of equations with four equations and 4 unknowns, and we want to solve it using Gaussian elimination. The augmented system is given by this, where we have moved the right hand side to the left, and we haven't yet and we are going to operate on this using Gaussian elimination, but first step will be the reduction, and then we will use back substitution to solve this system. So, in the first step, we want to eliminate the coefficients of x in the second equation, right. So, this 4x, we want to get rid of this 4x. So, what do? We divide the first equation by 2, because 2 is the coefficient of x in the first equation. We multiply after dividing the first equation by 2, we multiply the first equation by 4 and subtract that from the second equation. Similarly, we multiply the first equation by 2 and subtract it from the third equation, and so on and so forth. So, if we do that, the multipliers for equation 2 is a21 by a11, which is 4 by 2 is equal to 2, 4 by 2 is equal to 2. The multiplier for equation 3 is a31 by a11, so 2 by 2, that is equal to 1, and the multiplier for equation 4, where the coefficient of x is 0, is nothing but 0 by 2, which is equal to 0. So, if we subtract m21 times equation 1 from equation 2, m31 times equation 1 from equation 3, and m41 times equation 1 from equation 4, then we are going to get this system. This is the reduced system at the end of the first step, where you can see that the second equation now has 0 coefficients. It has got a 0 coefficient as on the first column. So, the coefficient of x1 is actually equal to 0. In the second step, we want to eliminate the coefficient of y from the last two equations. So, this is the coefficient of y. So, I want to eliminate this from the last two equations. So, what do? I divide the second equation by 2, and then I multiply the second equation by -2 and add it to the third equation. I multiply the second equation by 2 and add it to the fourth equation. And if I do that, so basically my multipliers now are A322 by A222. So, -2 by 2, which is equal to -1 for equation 3. For equation 4, my multipliers are A422 by A222, which is 2 by 2, which is equal to 1. And then I obtain my reduced system by multiplying equation 2 by M32 and subtracting it from equation 3, by multiplying equation 2 by M42 and subtracting it from equation 4. When after I do that, this is my system. This is my resultant system, and as you can see, this system is triangular, right? If you look at my coefficient matrix, it is a triangular system, and this can be easily solved using back substitution. It actually, for if this matrix were different, we might have had to do a third step, but the structure of the matrix is such that even after 2 steps of reduction, we get a fully triangular system, and we can go ahead with our back substitution and can solve this system. So, before getting any further, let us do an operation count. Basically, we want to count the number of operations involved in Gauss elimination. Why do we want to do this? We want to get an idea of the rate of increase in computational cost with the size of the matrix. So, as n increases, how quickly does the computational, what is the rate of increase of the computational cost? That is what we want to find out. To do that, we have to count the number of operations in each step. We recall that step A, k, involves n minus k equations in n minus k variables. For instance, when the first step, after the first step, we have n minus 1 equations and we have n minus 1 variables. The second step has n minus 2 equations, n minus 2 variables, and so on and so forth. Each coefficient of the first equation are divided by the first coefficient. Hence, n minus k plus 1 divisions are required, because there are n minus k terms, and then there is the right hand side also. So, there are n minus k plus 1 terms, and each term in that first equation has to be divided by the first coefficient. So, there are n minus k plus 1 divisions are required. Next, the scaled coefficient of the first equation are multiplied by the first coefficient of the remaining n minus k equations, and the results are added to the existing coefficients. So, what does that mean? That means there are n minus k times n minus k plus 1 multiplications and additions. Why? The first equation was done, we disregard the first equation. So, now there are n minus k equations, but for each n minus k equation we have to do n minus k plus 1 multiplications and additions. So, n minus k times n minus k plus 1 multiplications and additions are required. For large values of m, the cost of the n minus k plus 1 divisions are negligible compared to the cost of the n minus k times n minus k plus 1 multiplications and additions. Why is that? Because this involves square terms, right, n square terms. So, the cost of this is negligible compared to the cost of the n minus k plus 1 divisions. Hence, neglecting the divisions, the total number of operations is n minus k times n minus k plus 1, but remember this has to be performed for each step in the reduction, and there are n minus 1 steps. So, we sum over k is equal to 1 to n minus 1, and if we do that we get 1/3 n cube plus half n square p minus 1. P is of, remember, is the number of right hand sides. For sake of simplicity, if we assume that the number of right hand sides is 1, so we have 1/3 n cube, approximately 1/3 n cube operations for large n. Even if p is not 1, 1/3 n cube would be much greater than half n square times p minus 1, again because n cube is much greater than n square. So, the total number of operations is about 1/3 n cube for large values of n. So, once we have obtained a triangular system, to solve the triangular system it takes n divisions, and as we saw earlier it takes half n minus 1 times n additions or multiplications, which is approximately equal to half n square operations, half n square additions and multiplications. Hence, the back substitutions for large systems requires half n square additional operations. Since for large systems 1/3 n cube, recall that from our previous slide 1/3 n cube is the total cost of the reduction. 1/3 n cube is always going to be much larger than half n square for large systems. So, the major cost in Gaussian elimination lies in the reduction to the triangular system. So, if we want to speed up the cost of Gaussian elimination, we have to find out cheaper ways to do the reduction. We have to cut down the cost of the reduction, and there are several ways of doing that. We are going to talk about some of them later on. But recall that during our discussion of Gaussian elimination, we always impose the condition that the pivot, the term by which we divide those equations, the terms by which we normalize the equation. For instance, let us go back and look at our equations again. So, these pivots, right, A222, or for instance in this case A11, these pivots have to be non-zero. If they become 0, then this procedure stops, it cannot proceed, we cannot proceed with our reduction procedure. So, the prerequisite for Gaussian elimination to work without any interchange of rows or columns is that these pivots must be non-zero. So, from the algorithm for Gaussian elimination we have considered so far, it is evident that if any of the terms A11, A222 or A333, all of these terms are the pivots, right, the terms by which we normalize the equation. If these are 0, then our algorithm is going to fail. Hence, all practical applications of Gaussian elimination require some pivoting, because we cannot be assured that these terms are not going to be 0. To understand how pivoting works, let us consider the system, the simple system, 3 by 3 system in 3 unknowns. X1 plus x2 plus x3 is equal to 1, x1 plus x2 plus 2x3 is equal to 2, and x1 plus 2x2 plus 2x3 is equal to 1. After the first step of the elimination, we get 0x2 plus 1x3 is equal to 1, and 1x2 plus x3 is equal to 0. Since the coefficient of x2 in the first equation is 0, this algorithm is going to break down because the pivot is 0. However, the problem is resolved if we interchange the rows in the above equation. So, if we interchange the rows in the above equation, since the coefficient of x2 in the second equation is positive, we can again proceed with the reduction. In general, let us generalize this. So, in general, suppose at step k in our reduction process, we find k is equal to 0. In that case, there will always be some other element in the kth column, suppose ARKK, which is non-zero. Let us go back and look at our previous example. In this case, A22k is 0, but A32k is not 0. So, that is why we can interchange these two rows to make sure that the pivot is no longer 0. Why are we assured that there must be at least one element in the kth column which is not 0? Because if all the elements in the kth column is 0, this implies that the first k columns are linearly dependent, because we have formed the kth column to reach the kth step we have formed, and to form the kth column we have formed the kth column by taking scalar multiples of the first k minus 1 columns. So, if the kth column, if all the terms in the kth column are 0, it only means that I can get the first k minus 1 columns are linearly dependent. Recall our discussion of linear dependence and linear independence from our previous lecture. So, if k minus 1 vectors, if we can add k minus 1 columns, that is k minus 1 vectors, if we multiply each column by a scalar and we add them together and the result is 0, we say that those first k minus 1 columns are linearly dependent, they are not linearly independent. And if they are linearly dependent, what does that mean? That means that matrix, that coefficient matrix A is singular, because it has got its rank is less than n. But since we have assumed that the matrix is non-singular, that means that it has got full rank, that is, the kth column cannot be obtained as a linear combination of the first k minus 1 columns. So, we are assured that at least some elements in the k minus 1 column must be non-zero, otherwise the matrix is singular. Since at least one of the elements in the kth column is non-zero, we can always interchange that row with the kth row to restore non-zero, to make sure that our pivot is not 0, and we can continue with our reduction procedure. Since ARKK is non-zero, we can interchange rows R and K and proceed with the elimination. Thus, it follows that any non-singular system of equations can be reduced to triangular form by Gaussian elimination accompanied by row interchanges. If the system is singular, there is no assurance this can happen, because we can get eventually a row which has got 0 entries, all 0 entries, and in that case we can no longer get a non-zero pivot. However, it is not always true that only if the pivot term is 0 it is necessary to do pivoting. If the pivot terms becomes really small, it becomes sufficiently close to 0 that if we divide the equation by that pivot term, we are going to get numerical instability. In that case also, it might be necessary to do pivoting. So, it may be necessary to perform row interchanges not only when the pivotal element is exactly 0, but also when it is nearly 0, in order to improve numerical instability. To see the need for this, we consider the previous system which we considered earlier, but in this case we change the coefficient of A22 from 1 to 1.0001. Let us take a look at our previous system. So, here the coefficient of A22 was 1. So, instead of keeping it 1, let us change it to 1.0001 and see what happens. If we do that, we will see that our triangular system after Gaussian elimination is going to become something like this. And if we do back substitution and using round off after 3 decimals, so we will get x1 equal to 0, x2 is equal to 0, x3 is equal to 1. However, the true solution, if we use 4 decimals, if we round to 4 decimals, is actually x1 equal to 1, x2 equal to minus 1.0001, x3 is equal to 1.0001. So, we can see by using a nearly 0 element as the pivot, our system of equations has got a totally erroneous solution. Why? Because when we used a pivot 1.0001, our system became ill conditioned. So, minor perturbations gave totally different solutions. So, if instead of using a near 0 pivot, if we did pivoting, if we interchange the rows to get a sufficiently large pivot, we would have got the true solution. So, it is very important to do pivoting not only when the pivotal element is fully 0, but when the pivotal element is nearly 0. It is clear that without interchanges, Gaussian elimination is going to be inherently unstable and will give rise to meaningless results. However, by interchanging rows 2 and 3 in rows 2 and 3 in this equation, we could, and again using 3 decimal points in our computations, we could get x1 is equal to 1 and x2 is equal to minus 1.0001, which is almost exactly the true solution. Thus, it is clear that interchange of rows is essential in order to obtain accurate solutions in such situations. Now, let us talk about 2 particular types of pivoting. First, we want to talk about partial pivoting. If the interchange of rows is extended to make sure that we interchange the kth row with the row that has the largest element in the kth column, it is known as partial pivoting. This is clear if we look at this little picture. Suppose we are looking at this system, we have reduced it up to here. So, it is a triangular system up to here, and this is our, and we are left with this system, and we want to reduce it further. And we look at the pivotal element here, and we find that the pivotal element is either 0 or sufficiently close to 0, so that we need to do pivoting. So, what do? We look at all the elements in this shaded region. That is, basically we look at all the elements in this column, and we select the element which has got the largest non-zero magnitude, which has got the largest absolute value, and then we interchange this row with the top row. So, we interchange this row with the top row, so that our pivot, we get the largest with the best estimate we can of the pivot. So, in order to avoid ill conditioning, and then we proceed with the rest of our operations. So, the partial pivoting basically requires that we choose R here such that mod of ARKK is the maximum in that column. Over k equal to 1 through n, this term is the maximum in this column, and after we find the maximum element in this column, we interchange this row with our kth row. So, this is known as partial pivoting. We also have something known as complete pivoting. In complete pivoting, we not only interchange the rows, we also interchange the rows and columns. Instead of restricting to the kth column to find the element to interchange with the current AKKK, the search is extended to other columns also. So, AKK is replaced by the element with the largest magnitude in the partition. Basically, let us look at our picture in the next slide. So, now again suppose this is my near 0 element or 0 element. So, instead of that, instead of finding the maximum element in this column, we find the element which has the maximum magnitude in this entire partition. That is, we look over all the rows and columns in this partition, in this shaded region, and find the maximum element, and then we interchange this column with that column and this row with that row. So, basically instead of restricting to the kth column, we find the element to interchange with the current AKKK. The search is extended to other columns also. So, we extend the search to the other columns, and AKKK is replaced by the element with the largest magnitude in the entire partition. So, it is replaced by the largest element in the entire partition. Thus, complete pivoting requires that we choose R and S as the smallest integers which satisfy ARSK is equal to maximum of AIJK, K is lesser than equal to I, J is lesser than equal to K, and interchange the rows R and S and the columns K and S. Complete pivoting therefore requires searching over the n minus k plus 1 elements of each of the n minus k plus 1 columns of the partition to determine the pivot. Thus, complete pivoting is much more expensive than partial pivoting, because we have to search over all these elements in the entire partition. In practice, however, partial pivoting is usually sufficient to prevent numerical instability and is commonly adopted. Thank you. We will continue with our discussion of Gaussian elimination. In particular, we will look at some particular algorithms for doing Gaussian elimination, for instance LU decomposition, crowd factorization, etc., which can further reduce the cost of Gaussian elimination by making it more efficient and more compact.